list the things. Let's see, and I didn't label that other. This is 919. So I like to list the things that I know that might be useful, or what I need to know. I need to know the area, because I'm going to have to calculate stress, strain, total elongation. So on the stress and strain, I'm going to need the area, right? So the area is 2 by 2, right? 4 square inches. Then I need to know, or they tell me, don't they tell me the length? Oh, I'm looking at the wrong problem, sorry. It's not 4 inches. I was looking at problem number 15. I think I still need to know the area though, don't I? See, 19, yeah, I still need the area. I was just looking at the wrong problem. Pi times the diameter, 25 squared divided by 4. Probably got that memorized by now, don't you? 490.87, or you could say 490. That's there again. That's a case where if you're doing this at home on that test, you might have just said 491, and it would be fine. I said 490.87. We're going to come up with different answers. Oh, well, we definitely would come up with different answers then, wouldn't we? Thank you. 7 millimeters squared. Okay, what else do we know? We know its length is 4 meters, or 4,000 millimeters, right? Or you could say 4 times 10 to the third. We know that the p-value, the force, is 65 kilonewtons. Or, and I didn't do this, but you might even say, what, 65 times 10 to the third newtons, because it needs to be in newtons, doesn't it? It needs to be in newtons and millimeters. And you could have said 4 times 10 to the third millimeters, right? Same thing. Let's see, do we need anything else? Or do we know anything else? That's about it, right?
No, it's aluminum,
so we could, are we going to need the modulus?
Yes.
Yeah. So
I was going to ask you about that. I took the 10 million psi for aluminum and then multiplied that by the number in the front of the book here, 0.006895, to get my megapascals. It looks like you just used 70,000.
70.
I guess it's just a rounding issue again. Pull that out.
What did yours come out to?
Well, I got 68,950 megapascals.
Mm-hmm. Right. The metric units are on page 502.
I missed something in the chart, another chart in the back.
So the aluminum alloy is 70 times 10 to the third megapascals on page 502. And I didn't actually mark that in the solutions. So, I put where I looked at that other thing, but I didn't put that one on
No,
there.
I took the conversion factor out of the front and used that, and you used the chart.
Yep.
Easier, I guess.
Well, it's easier, but then, like you said, there could be a rounding error at that point, because you're using a number that is rounded, the point whatever, like that conversion factor.
Yeah.
So there would definitely be a rounding error issue there if you had done it that way. It should still come out pretty close, though.
Yeah, mine was close.
Yeah.
Just a little off.
Yeah. And there again, come test day, if you had done that, I'd have to go back and look at it and make sure that everything's good. But we'll do that. So yeah, that modulus comes from the page 502, and it's 70 times 10 to the third, wasn't it? Mm-hmm. Megapascals. Okay, I didn't write that in my solutions as far as something that we would know. I didn't put that down. I just used it later on. So we need to know the stress, the strain, and the total deformation. That's what we're looking for, right? Why does that? There we go. Okay, let's see if we can roll that up a little bit. All right, so let's see, what do we do for A? Well, we already, let's see, for A, we want to find the stress, and that's going to be the the force, which is 65 times 10 to the third newtons divided by the area, which we said was 490.87 millimeters squared, as opposed to inches squared. Caught me. Thank you for catching me. That's it. That's all you have to do on this one. It's almost scary. It's too easy, huh? 132.4 newtons per square millimeter, or 132.4 megapascals. And there again, well, and if you don't have to worry about the units on the quiz, and that's why, I mean, you could either have newtons per square millimeter or megapascals, couldn't you? Either one would work. Typical, I think, more of the megapascals, and if you look back in the charts, that's what they give you everything as, right? So that's the first part. That's A. B, what are we looking at there? We're trying to find the strain. Well, let's see, for strain, what are we using for the equation? Stress over the modulus. Looks like.
So the strain is lower kc and the modulus is an upper kc, right?
Well, that's Greek for epsilon, I believe, isn't it?
It's like a cylinder line.
It's not really. It's not really an E. This one isn't. This one is.
Okay.
Okay, that one's a Greek epsilon.
Gotcha.
Okay, and let's see, where did we find that equation, in case you needed to know? If you looked on page 189, it's equation 9.8. It's about 2/3 way down in the left column. It's a rearrangement of that. The modulus equals the stress over strain. So if you're looking for, if you've got the modulus and you've got the strain, or the stress, then you're looking for the strain, right? So it's just a rearrangement of that equation. Make sense? So we just plug those numbers in. We just found out 132.4, and I don't know, how did I write that? Megapascals over that modulus, which was 70 times 10 to the third. 0.00189, and you could go farther than that if you wanted. Or what? 1.891 times 10 to the negative third.
Is that what we express in milliliters per milliliter?
That, yeah, and I put megapascals. It would be, yeah, that's, what would the answer for that be? As far as the metric units, actually that's going to be Yeah, it would be megapascals over megapascals, and it, you know, it's a kind of a unitless deal there.
Yeah, cancel.
Well, the megapascals should cancel each other.
Yeah.
The megapascals cancel each other, but then you're left with 10 to the third.
But after the megapascals.
So wouldn't it just be a Newton? It would just be a Newton, 1 point.
I don't think the strain. What is the
Could you still have the 10 to the third on the bottom, so isn't that just the same as a
That's
Newton?
just saying that there's 3 zeros there.
right? That's just
That's,
a
that's the
placeholder, if you will. Looking for the units for that. Yeah, since if you look on page 187, since the strain is a ratio of two lengths, it is dimensionless and considered a pure number. Common practice, however, to express strain in terms of inches per inch or, let's see, millimeter per millimeter, or meter per meter, depending on what your unit is. Okay. So, I guess that would be better if I had said, if I can find it again, there it is, millimeter per millimeter. But it's all I'm looking for there is that number. Okay. So again, it's a matter of I had to find the stress to figure out what that modulus was, or to figure out what the strain was. Excuse me. We had the modulus. Now then, let's see for C. We've got everything we need for. Well, no, we just found out for C we have to use that to find out what the deformation is, right? Total deformation is strain times the length. And if you were looking for the application of that equation comes from page 188. It's equation 7.9. The strain equals the deformation divided by the length. So then we rearrange that equation to get what we've got here. Okay. Plug the numbers in. Well, we've got the numbers 1.891 times 10 to the negative third times 4 times 10 to the third, which is the length, right? It was 4 meters. And that comes out to 7.56 millimeters. That's how much it deformed. So when you got done, let's see, on that problem was that it just says it's subjected to an axial tensile load of 65 kilonewtons. So if it's tension, it's going to grow, right? If it's compression, it's going to get smaller. That might be another step of the question, wouldn't it? What's going to be my final length? Well, then you would have to know, is it compression or tension? And you'd either have to add or subtract. Because that's where it really matters, isn't it? You know, I need to know that total length if you're putting some kind of force on there, because it might accidentally interfere with something else in your total mechanism. So if you're building one of those Rube Goldberg projects that, you know, you're subjecting some tensile stress to, it's going to grow and it might not clear what you want it to clear. Just a thought. What else? Does this we okay here? Jabril?
I didn't see when you were using 70,000 for E.
What about it?
I didn't see where you get it from.
That was like page 502, I think it was, wasn't it, in the back of the book?
Yep. 502.
502 is the metric version, okay, of aluminum alloy. It's about 2/3 of the way down in that chart in the second column from the left. And that's modulus of elasticity in megapascals, and it's 70 times 10 to the third. Hey, we got to know these kind of things, don't we? For Monday.
What equation did we rearrange to do C?
C was the equation that's on page 188 that says that the strain equals the deformation over the length.
A little S mean next to that.
Do what?
What's the sub-S mean?
Yeah, the sub S on that, what's that mean?
The sub S, well, let's see.
Shear.
Yeah. Shear strain.
Shear strain of it.
Mm-hmm. Which is depicted in that figure 916B.
On 187, it has the same equation without the sub S.
Okay. In the example problem 914. Well, yeah, equation 9.6. Yeah. Total deformation by the original length, and that's what the strain is. And then you just rearrange it.
Yeah.
So you'll want your book handy so you can look over those equations, or you're going to have to make up a little cheat sheet with all your equations on it. Might be easier, you know.
I wrote down a number wrong.
Wrote down.
I wrote down 0.25 millimeters instead of 25 millimeters. Because I'm like, I did it right.
Well, you know what?
Come out wrong.
In the solutions manual, he had it as 2.5.
Oh, really?
Yeah. So interesting. That's because it's like, wait a minute. Ah, crap! I forgot. I got to get him a test.